Time travel is one of humanity's most fascinating and complex concepts. This idea has persisted both as a theme that stretches the imagination in science fiction works and as a physical theory explored in the depths of scientific research. Whether traveling backward or forward in time is possible challenges the boundaries of disciplines like general relativity and quantum physics. Particularly, the universe models proposed by mathematician Kurt Godel and the time paradoxes highlight the complexity and potential logical contradictions of the concept of time travel. Kurt Godel was born on April 28, 1906, in the city of Brunn, within the Austro-Hungarian Empire. As a child, he was noted for being a very intelligent and curious student. In 1924, he entered the University of Vienna, where he studied mathematics, physics, and philosophy. He completed his doctorate in 1929, and in 1931, at the age of 25, he published his incompleteness theorems, which shook the world of mathematics. These theorems demonstrate the limits of mathematical systems and reveal the fundamental problems of formalism. The first of the two main theorems shows that in a sufficiently powerful and consistent mathematical system, there are statements that cannot be proven within the system. The second theorem proves that such a system cannot prove its own consistency. These theorems have become foundational in mathematical logic and philosophy. They dealt a significant blow to David Hilbert's program, ending the hope that all mathematical truths could be proven and computed. Gödel's work also had profound effects on computer science and artificial intelligence. Albert Einstein's theory of general relativity posits that space and time are curved by mass and energy. In 1949, building on Einstein's general theory of relativity, Kurt Godel proposed his own model of the universe. This model, based on a specific solution to the general relativity equations, suggested that the universe has a cyclic structure. Gödel's solution, known as the Gödel universe, includes closed time-like curves. These curves mean that an object or person could theoretically travel in a loop in time, returning to their starting point. In other words, these curves theoretically indicate that time travel is possible. Closed time-like curves could allow a person to return to their own past and even interact with their past self. To understand closed time-like curves, let's consider a story. One day, Jack successfully travels in a time machine. He operates the machine and goes back to his childhood. There, seeing young Jack, he gives him some important advice. He then returns to his own time. Jack remembers receiving this advice from a stranger when he was a child. Years later, he realizes that this stranger was actually himself and decides to travel back in time to give the same advice. This creates a time loop. This story is a simple example of a closed time-like curve. Jack travels in a loop in time, returning to his past, and this loop continues indefinitely. Closed time-like curves also bring some paradoxes. The grandfather paradox is one of the most significant. If Jack goes back in time and kills his grandfather when he was young, Jack's birth becomes impossible. However, if Jack is not born, he cannot kill his grandfather. This is a paradox and has led to many philosophical and scientific debates about closed time-like curves. These curves form by the curvature of spacetime under certain conditions, causing time to acquire a cyclic structure. General relativity is a theory that suggests space and time are curved by the presence of mass and energy. Gödel found a specific solution to this theory, revealing a cyclic time structure and closed time-like curves. In Gödel's solution, the universe rotates cyclically. This rotational motion causes time to acquire a cyclic structure at every point in the universe. Gödel's equations show that such a universe is mathematically consistent and compatible with the principles of general relativity. In the theory of general relativity, the speed of light is considered the highest speed limit in the universe. This means that no information or matter can travel faster than the speed of light. While working on this fundamental principle of the general theory of relativity, Gödel accepted the concept that the speed of light is the universal speed limit. In the theory of general relativity, the influence of an event on other events within its light cone is known as causality. The light cone is a geometric structure that shows all the points an event can reach at the speed of light. Any point within the light cone has the possibility of events occurring that either happen before the event or are not affected by it. These points are in the causal past of that event. The principle of causality is one of the fundamental principles of the theory of general relativity, ensuring that an event maintains a cause and effect relationship. The existence of closed time-like curves may seem contradictory to the principle of causality. Because closed time-like curves allow returns in time, this can complicate cause and effect relationships in time. The result of an event can simultaneously be the cause of a previous event, or an event can influence its own outcome. There is a significant relationship between the Koshi horizon and closed time-like curves in the context of the theory of general relativity. These concepts help us understand the mathematical and physical implications of the theory of general relativity and are important for understanding how spacetime is shaped. The Koshi horizon is an important concept in the theory of general relativity that shows how the effects of an event propagate to other events. At any given moment, the Koshi horizon of an event represents the distance that signals traveling at the speed of light from the event can reach. This horizon allows an observer to see how events interact in their domain, showing how the effects of an event propagate through spacetime. Closed time-like curves, on the other hand, allow a specific point in the time curve to return to its past. This is important for understanding the complex causal relationships of spacetime. The coordinate system in Gödel's universe is based on a special arrangement of time. This arrangement means that time does not progress at the same speed and simultaneously at every point. In other words, time can flow differently at different points in the universe. This structure implies that events do not occur simultaneously throughout the universe. Kurt Gödel's universe model and closed time-like curves have led to intense discussions in both philosophical and scientific circles. These discussions involve fundamental issues such as the nature of time, the structure of the universe, and whether time travel is possible. Gödel's theory suggests that time does not flow linearly and can be cyclical. This means that time has a structure without a beginning and an end. This idea challenges the classical understanding of time and raises deep philosophical questions about the nature of time. Closed time-like curves support a deterministic model of the universe. If time is cyclical, future events are determined by past events. This leads to debates about the existence of free will. In a universe where time is cyclical, whether individuals act with free will becomes an important philosophical issue. The existence of closed time-like curves may require extremely dense energy and mass conditions. Such conditions may be impossible or extremely difficult to create in practice. Additionally, modern cosmology shows that the universe is expanding, which contradicts Gödel's cyclical universe model. This raises questions about how well Gödel's model aligns with physical reality. Gödel's universe model is based on classical general relativity theory. However, efforts to unify quantum mechanics with general relativity raise new questions about the possibility of closed time-like curves and time travel. Quantum mechanics allows for re-evaluating the possibilities and limits of time travel. Gödel's cyclical universe model does not align with observational data. Modern astronomical observations show that the universe is expanding and this expansion is accelerating. Gödel's model, on the other hand, predicts a static and cyclical universe. This creates a significant scientific debate about whether the model aligns with observational reality. Time travel is one of humanity's greatest dreams and has attracted interest in many areas, from science fiction works to the scientific world. However, this concept presents serious physical and philosophical challenges within the framework of the theory of general relativity. Although Einstein's equations offer solutions that make time cyclical, such journeys are not practically possible and can bring about serious issues like time paradoxes. Don't forget to subscribe for brand new scientific content.